Okay, in the last class we discussed about heat, work and we defined them. So, in the last class we discussed work, we discussed heat, we discussed first law of thermodynamics, and we also discussed how to calculate work done. So, we know work done is minus P external times volume change, and this is true for irreversible process that we already know. And for reversible process, W is nothing but minus P times dV. We can substitute the value of P depending on the type of gas. For ideal gas, P is, we know, A naught T by V, and if we substitute the value of P, we get W is minus A naught T ln V2 by V1, where V2 is the final volume and V1 is the initial volume. And this expression is varied for ideal gas and isothermal process. This is for isothermal process. We also discussed and we also proved that W work done is a path function and internal energy U is a state function. Then we discussed about the work done for adiabatic reversible process and we ended up with an expression like P V to the gamma is constant, where gamma is Cp by Cv, that we know. Okay, so today we will start with what would be the work done for irreversible adiabatic processes. Okay. So, work done for adiabatic irreversible processes. So, there can be two cases. One is when there is no external pressure. So, when there is, so case 1 is when there is no external pressure, that is P external is 0. In that case, this is the simplest case one can think of. So, in that case we get W is minus P external delta V, that is the general expression for calculating work done. So, you get 0. Okay, so work done is 0 and the process is adiabatic one. So, Q is also 0 as the process is adiabatic. So, from first law of thermodynamics we can write del U is 0. So, there is no temperature change, okay, because internal energy for an ideal gas depends on temperature. Since there is no internal energy change for this process, so there is no temperature change. And then in the next case, we will consider that when external pressure is not 0, so we get W like this. So, we can write this is nothing but okay, and we can write delta U equals to W for adiabatic process we know. So, we can write like this. So, we considered three different cases for calculating work done. First is isothermal reversible process, where W we can write like minus n RT ln V2 by V1. Then we considered work done for adiabatic process, and for work done in adiabatic process we will have two different types of work done. Like first one is isothermal process, first one is reversible process, and for reversible process we get PV to the gamma is constant, and for irreversible process we get two cases. When the simplest case is when the external pressure is 0, in that case we get there is no internal energy change and there is no work done also, and when external pressure is not 0, in that case we get this expression Cv T2 minus T1 equals to P external times RT1 by P1 minus RT2 by P2. Okay. Next, what we do, we will compare the work done between isothermal and adiabatic expansion. So, we will start with we will consider that we consider ideal gas. Okay, ideal gas, and we consider that Vi is the initial volume Pi is the initial pressure and Vf is the final volume. And P iso is the final pressure for isothermal expansion. And P adia we consider as final pressure for adiabatic expansion. So, we started with same initial volume and same initial pressure, and we reached to same final volume for both isothermal and adiabatic processes. So, pressure has to be different. So, we will calculate final pressure for isothermal expansion and final pressure for adiabatic expansion. Okay. Once we get that, we can easily calculate the work done for isothermal process and work done for adiabatic process, and then we can compare between them. So, for isothermal process, we know we already discussed in the last class. For isothermal process, we know PV or P1 V1 equals to P2 V2. So, he says that Pi Vi so this is from Boyle's law. We know that for isothermal process Pi times Vi equals to P iso times Vf. For adiabatic process, we know for adiabatic process P 1 V1 to the gamma equals to P 2 V2 to the gamma. So, we can write similarly like P I Vi to the gamma Okay, so these are the expression we get. Okay. Now, from here we can write P I by P iso like this, and from here we can write like this. Okay. Now, we know that gamma is nothing but Cp by Cv, and it is greater than 1 for most of the cases. Because Cp is greater than Cv for most of the cases that we know. In that case, we can write that Vf by Vi to the gamma like this. Okay. So, we get this. So, this tells us that Pi by P adia is greater than Pi by P iso. Okay. So, we get that P iso is greater than P adia. So, what do we get? We get that we started with same initial volume for both the processes, and we reached to the same final volume. Okay. Initial pressure was also same for both the processes, and we obtained that for isothermal process the final pressure is higher than that adiabatic process. So, if we draw whatever we discussed in a simple PV diagram, it will look like so. This is for isothermal process, and this one is for adiabatic process. So, this is our initial pressure, this is Pi, this is our P iso, and this is our P adi. So, if we label them as like A, B, C, D, E. So, for isothermal process, work done is nothing but area under the curve A, D, C, B. Similarly, for isothermal, for adiabatic process, the work done is represented as area under the curve AECB. Okay. So, since the area for isothermal process is higher than that of adiabatic process, so work done for isothermal process is greater than work done for adiabatic process. Okay. So, if we carry out a process in isothermal manner, then we get more work done than that of adiabatic process. We can do very similar exercise by starting with same initial volume. Similarly, we can prove similar fashion. If we started with same initial volume, same initial pressure, and if we reach to same final pressure, and if we say that final volume for isothermal process by, if we represent the final volume of isothermal process by V iso, and if we say V adia is the final volume for adiabatic process, we will get a curve like this. We get like this. Okay, so far we have discussed or we have compared the work done for isothermal process and work done for adiabatic process. Now we will discuss about enthalpy. So what is enthalpy? Enthalpy we denote by H. Okay. So what do we mean by enthalpy? Next question is. Okay, so in enthalpy we can define it like this. It is equal to the energy transferred as heat in a constant pressure process. This is very important. Involving only PV work. So, last part of this statement is very important. So, enthalpy can be defined as the energy transferred as heat in a constant pressure process involving only PV work. Okay. So, from first law of thermodynamics we know delta U is Q plus W, and we can further simplify it like this. So, if the process is carried out at constant volume, means there is no change in volume for a process, then we can write delta U is nothing but QV. The subscript V stands for constant volume process. So, constant volume means V1 equals to V2, there is no volume change in that process. Okay, so, we can calculate internal energy change for a process by measuring the heat change, provided the process is carried out at constant volume. But we know that many of the chemical reactions are carried out at constant pressure process. Okay. So, how do we calculate the energy or heat change for that process? Okay. So, it would be convenient to have a state function very analogous to internal energy U, so that we could write an expression like this equation 1. Okay. So, for constant pressure process, now let us see what happens if the process is a constant pressure process. For constant pressure process, delta U is Qp plus not plus, this minus rather, minus P times V1 to V2 dV. So, we get QP is nothing but delta U plus P delta V. Okay. So, for a constant pressure process, heat change, if we denote the heat change as QP, we get this expression. Okay. So, by definition, this QP is nothing but enthalpy change for that process. So, we can write this is nothing but delta H. Okay. So, what we got, we obtained that delta H is nothing but delta U plus P delta V. Okay. Okay. And for we can further simplify this one as delta U plus delta N G R T, where delta N G is the change in the number of moles of gaseous product minus number of moles of gaseous reactants. For example, into when 2 moles of nitrogen reacts with 3 moles of hydrogen, both are in gaseous states, when it produces 2 moles of ammonia gas, in that case delta Ng is 2 minus this is one example. Second example is like you can consider H2 so delta Ng for this reaction is minus 3, because the molar volume of liquid water is much smaller than the molar volume of gas. Okay. So, molar volume. So, we can safely ignore this 2 term here. Okay. So, since molar volume of liquids are much more smaller than the molar volume of gases. Okay. So, this is how one can calculate delta N G. Okay. Next, we move to heat capacity. How or what do we mean by heat capacity? Okay. Okay, so heat capacity is defined as the amount of heat required to raise or to increase the temperature of a substance. So, the amount of heat required to increase the temperature of a substance by 1 degree or 1 Kelvin. Okay. So, heat capacity, it is defined as amount of heat required to raise the temperature of a substance by 1 degree. So, heat capacity we in general we term as C. So, C is nothing but du by dt. Okay. Now, whether it is an extensive property or it is an intensive property. Okay. So, heat capacity depends on the amount of heat required to raise the temperature of the substance by 1 degree. It depends on the amount of substance. So, it is an extensive property. Okay. So, heat capacity is an extensive property because the amount of heat required amount of heat required to raise 1 degree depends on amount of substance. Okay. So, heat capacity is an extensive property. Okay. But heat capacity per mole or molar heat capacity is an intensive property, but now next question is whether heat capacity is a path function or is a state function. Heat capacity in general is a path function. So, heat capacity in general is a path function because we get different heat capacity value if the process is carried out in constant volume process or in constant pressure process. Okay. So, heat capacity depends on whether the process is being carried out at constant volume or at constant pressure. In both cases, we get different heat capacity values. Okay. So, heat capacity in general is a path function, but heat capacity at constant pressure Cp or Cv, they are state functions. Next question is why Cp and how do you define heat capacity at constant volume. We define it by, and we just have seen that this is nothing but is delta U by delta T, or we can write this as QV by delta T. Okay. We have just seen this. What about heat capacity at constant pressure? So, we define it as Cp nothing but okay. So, and we know Cp is always greater than, in most of the cases rather, greater than Cv in most of the cases. Okay, so what is the relationship between Cp and Cv? Next we will discuss. Okay. Very simple derivation we can carry out. So we know U, internal energy U is function of pressure and temperature. So we can write du So this is, suppose this is our equation 1. So we know U is function of pressure and temperature. So du we can write as del U by del P at constant temperature times dP plus del U by del T at constant pressure times dt. Similarly, E is also a function of U, internal energy is also a function of V and T. So we can write du in similar fashion. We can write du is del U by del V at constant temperature times dV plus del U by del T at constant volume dt. And we denote this equation as equation number 2. Again, V is also a function of pressure and temperature. If we change pressure and temperature, V also changes, right? We know. So we can write dV is like this. So dV we can write del V by del P at constant temperature times dP plus del V by del T at constant pressure dt. So this is our equation 3. Okay. So if we substitute the value of dV from equation 3 to equation 2, so substituting the value of dV of equation 3 into equation 2, we get du we get like this. Okay, we can further simplify this equation as and we define this equation as equation 4. Now, if we compare equation 1 and equation 4, we obtain del U by del P at constant temperature is del U by del V at constant temperature times del V by del P at constant temperature. So, this is our equation 5 suppose, and we also get del U by del T at constant pressure like this. This is equation 6. So far we have not introduced the term H or enthalpy. Now, if we introduce the term enthalpy H here, so we know H equals to U plus PV. Okay. So, we get UH minus PV rather. So, we get del U by del T at constant pressure is del H by del T at constant pressure minus P del V by del T at constant pressure. So, this is our equation 7. Okay. So, from equation 6 and 7 we obtained and 7. What we obtain is del H by del T at constant pressure minus P del V by del T at constant pressure is del U by del V at constant temperature times del V by del T at constant pressure plus del U by del T at constant volume. Okay. So, this is nothing but your Cp and this is nothing but your Cv. So, we get Cp minus Cv is P plus del U by del V at constant temperature times del V by del T at constant pressure. So, this is this expression we say 8 is this expression 8 is a general expression. Okay. So, expression 8 is a general expression. Is a general expression. Okay. So, we should remember expression 8 and ideal gas case is a special case. Okay. So, for ideal gas we know del U by del V at constant temperature is 0 and del V by del T at constant pressure equals to nR by P. Okay, how we are getting this? So, V is nRT by P gives you del V by del T at constant pressure nR by. So, for ideal gas when there is no temperature change, we get there is no internal energy change. Okay. So, if we substitute this in the previous expression, we get Cp minus Cv is nR, that we are familiar with. Okay. we know this expression from our +2 level. Okay. This is for n mole. Okay. And Cp minus Cv, Cp and Cv per mole gives you this expression. Okay. So, Cp minus Cv is equal to Nr for ideal gas, but we should remember the equation 8 carefully, because this is the general expression. Okay. It is an ideal gas case is a special case. Okay. That is it.